I want to make two comments. First, the importance of dispersion. There are two things that are probably important to think about. The dispersion is very important because when you try to design, for instance, of course, we'll talk a little bit about non-imaging optics next week, but this, when you try to design, let's say, lenses for a camera, like if you open up this camera here, that will have about 6 or 7 lenses. Now, as you learned last week, a lens typically is designed for one wavelength. If you try to illuminate it, use it at a different wavelength, its focal length will shift, it will have different aberrations and so on. It won't work as good. Now, it depends on the properties of the lens and so on. But you can use materials with 2 different dispersion, so like crown glass and flint glass, for instance, to compensate for the difference in the wavelength. So this is a very common use of lenses. So if you look at, you don't see them in the mobile phone lenses because they're all plastic today. But in the DSLRs, for instance, you use different kinds of glasses in order to compensate for the difference in the different wavelengths. So this is very important from that perspective. In the mobile phones, which is, of course, what the vast majorities of cameras are today, this is done a little bit differently with plastics and doping of the plastics and so on. Well, I don't know why my computer is flashing, but anyway. Let me. The last point I want to say also about the mirrors. So mirrors, of course, are, you don't think about them too much, but they're actually quite important for astronomical purposes because 2 reasons. Mirrors don't have dispersion, right? This is a very important observation to keep in mind. So the mirror, where the focus is formed, is simply a function of the shape of the mirror. There's no dispersion here because you don't have to obey the Snell's law. N doesn't come into any equation here, right? It's purely the law of reflection. So mirrors are great if you want very broadband performance. And typically this is useful in astronomical situations where people are looking at, very large bandwidths. You want to see, I don't know, X-rays from black holes to visible light from, interstellar medium or whatever. So in those situations, so for example, the Hubble is not a good example, but the James Webb telescope, which you might all know, is supposed to be launched, I think, early next year or something like that. It's going to be the largest space telescope in the world. It utilizes mirrors, not lenses like here. So these are lenses. So I should show that as a picture. Yeah, no. Oh, okay. So there's a lot of stuff here. So anyway, yeah. So this is a very simple Newtonian telescope. So light comes in, and you put a sensor there. Of course, this is problematic because the sensor is shadowing the mirror, right? So you're blocking some of the light. Anyway, there are lots of different ways to do this. It's a very rich area of research by itself. Now let's go to today's lecture, which actually is here. So any questions about geometrical optics before we move on? Okay. Feel free to message on Slack. Make sure you practice, and it will